All right, hey everybody, I am coming at you on campus. Kind of weird to be back, but I wanted to make sure our videos this semester, since we are required to be online, are really clear for you. So I went back through and looked at how we can do a better job. And I wanted to start with solubility. So we're starting with, it's chapter 11 in the OpenStax Atoms-First textbook. And I have a little PowerPoint, just slides to kind of help you anchor it. You can print those out, or you can have those open and make notes on them as you like as we go through. It's important that you, when you watch these videos, you engage with them just like you would in a lecture. So putting everything else away, all distractions, turn off your phone or hide it under something across the room so every alert isn't distracting you. All right, so let's talk about solubility. We're going to talk about it generally first, and then we're going to do a little bit deeper dive. All right, so we're going to start with some basic definitions. We're going to start with solute, solvent, and solution. Okay, solute, really generally speaking, solute is like what you are dissolving, or what is dissolving in typically a liquid solvent. It's usually the smaller amount. I wrote AMT for amount. It's usually the smaller amount. Solvent is our, again, typically liquid, not always, but typically liquid. That we're going to get a Department of Redundancy department here, but the liquid that our solute dissolves in. Dissolves in. All right, I know I ended with a preposition there, but hey, it's not English class, lighten up. All right, so the liquid typically that our solute dissolves in, and my favorite actually is solution. It's the whole shebang, everything. So this is your solute plus your solvent. Now these definitions become important because when we talk about different concentration units, sometimes we'll have a term for kilograms of solvent, and in another concentration term we'll have liters of solution. So it becomes important to know the difference because the number that you use will be different when we get to those calculations. All right, so let's touch on solubility. What does solubility mean? Technically, it's the maximum amount sorry, that was ugly. The maximum amount of solute that goes into the solvent kind of generally we will just say how much dissolves. This is a little bit more general. Technically it's the maximum amount under those conditions, and that depends on things like temperature and sometimes pressure, things like that. Okay, so those are our basic definitions of solubility. So solubility is the amount of solute that goes into the solvent or how much dissolves. Now, we talk about solutions as being homogeneous and heterogeneous. In the OpenStax, it says if a mixture is heterogeneous, it's not a solution. But I use that term along with mixture. I do define it as heterogeneous or homogeneous, but just a heads up, your book definition will be a little bit more precise there. So what I want to talk about are some other terms, miscible and immiscible. sometimes we're mixing two liquids together. So two liquids that mix completely are called miscible. And two liquids that do not mix, meaning liquids that form separate layers, are called immiscible. So what does this look like? I'm just going to draw a diagram. I had a hood alarm going off. Okay, so I'm just going to draw a simple diagram. So let's say we have water here, and I'm going to do two different experiments. I'm going to add ethanol to water, and what happens is, because ethanol is miscible with water, it completely blends, and you can't tell where the ethanol is and where the water is. The particles, the molecules of ethanol and the molecules of water are completely like commingled. We can't see where one ends and the other begins. However, if we add oil, or if you're from Texas, oil, if we add oil, then what we get is two separate layers, and water is denser, so the water will be on the bottom and the oil will be on the top. I should have used blue. Man, not feeling creative today. Bummer. Blue for water. Okay, and so this is what we would call immiscible, because they don't mix completely. We can see where one layer of liquid ends and another begins, and where they sit depends on density. When you get into organic lab, you're going to use this a lot. You're going to have you're going to use separatory funnels, and you're going to have a water layer, and you're going to have what we call an organic layer. Organic meaning carbon-based, and also nonpolar, which we'll get to in our next video. And miscible, again, is when we're mixing two or more liquids and they completely combine such that we can't see a separation in the two liquids. Okay, so pretty straightforward. We're just starting with some definitions. These are our general conceptual questions. Now let's get into dig a little bit deeper. Oh, I said it was in the next video, but actually it's in this one. Let's talk about like dissolves like. So this is our rule for solubility. Sorry, that's our hood alarm going off. Like dissolves like. It's really easy to say. But it's a little bit tougher to apply. And so this is where we kind of dig in from last semester. This is from last semester, 1410 at our college. Last semester, you need to be able to identify polar and nonpolar compounds. If you are not comfortable doing that, you need to pause and go back to the review videos identifying polar compounds, or polar versus nonpolar. Go back and review those, and then pop back over and you'll be ready. Okay, now if you're good, we'll just move on. Okay, like dissolves like, easy to say, but what does that mean? It's really based on polar and nonpolar. Polar meaning there's a separation of what we call electron density. The electrons in the compound aren't shared completely evenly. Someone is hogging those electrons, so a difference in electronegativity. All right, and so what we mean is polar solvents dissolve or blend or are soluble with or mix with. There are a couple of different synonyms here. Polar solutes. Okay, so that's one tenet or point of solubility, like dissolves like. The other is nonpolar solvents dissolve, mix with, blend nonpolar solutes. Okay, all right. And this makes sense. You can apply this to stains. If you get grease on your shirt, you're going to want to use something that has which is nonpolar. You're going to want to use a stain remover that is nonpolar. That's why water won't work. Water is polar, like the most polar solvent on earth. And so that's not going to get any grease off your shirt. I also heard someone say if you spill red wine on your carpet, you can try using white wine. I don't know why you'd want to waste any good white wine, but maybe, I don't know. Okay. So like dissolves like, simple concept. Now we need to apply it. So I have an example here. This is a hydrocarbon. Which carbon is more soluble in? Hydrocarbon means it has only carbons and hydrogens in the compound. So we call this a hydrocarbon. Hydrogen and carbon only in the compound. All right, and when I say more soluble in, that's telling you, the phrasing of that sentence is telling you this is the solvent. It's really that preposition in that tells us that's a solvent. Okay, and which is more soluble? Sodium chloride or carbon dioxide? Which is more soluble? I wrote out a couple of steps on the slide. What we need to do here is first identify if the solvent is polar or nonpolar. Then we're going to identify our two solutes as polar or nonpolar. And then we're going to match either polar with polar or nonpolar with nonpolar. All right, so let's get started identifying hydrocarbon. So you could take the time to draw out a structure. However, if I only have carbon and hydrogen in the formula, the only kind of bonds I'm going to have are carbon-carbon or carbon-hydrogen bonds. Are either of those polar bonds? Carbon and carbon, same element, can't have a difference in electronegativity, so that can't be a polar bond. And then carbon-hydrogen, they have very similar electronegativities. I think carbon is 2.5 and hydrogen is 2.1. But anyway, non-polar. There are no polar bonds, so hydrocarbons are always non-polar. Kind of a quick and dirty trick for you. Okay, so that means the solute that's more soluble is going to be the non-polar solute. All right, so let's take a minute. Sodium chloride, is it polar or non-polar? A couple of ways you can do this. You can identify it as an ionic compound. Ionic compounds are superpolar. Ionic is like the extreme of polar. Right? If we have a continuum of polar and non-polar, ionic is at the far end on the polar end of that spectrum. The other thing you could do is look up in a table Debye values. It's also called a Pauling chart, named after Linus Pauling. You can look up the values. When we teach online and we have, to stay at home, we do have open book, open note exams. So if that's something that's more comfortable for you, you can use it. When I have my students take the exam at the testing center, I don't provide that. I do write different exams because if you can't use anything but a periodic table, obviously the exam needs to reflect that. But when you have all open notes and everything, the exams are a little bit different. Okay, so ionic, polar. So is something polar going to dissolve in something nonpolar? Very little, if any. Very little, if any. All right, so carbon dioxide, you might see the carbon and oxygen and think automatically, oh, that's probably polar. Well, we have polar bonds. And again, if you're struggling with Lewis structures, pause right here, go back to Lewis structures, and then identifying polar and nonpolar compounds. That's a very important part of solubility. Okay, well, we do have polar bonds, a carbon-oxygen double bond is definitely polar. That oxygen is more electronegative. But what do we have going on over here, right? This is 180 degrees, right? This is linear because I have two things attached, 0 lone pairs. Okay, so these vectors actually cancel out. It's like a tug of war between two dogs, right? They have like this rope toy and they're both of equal strength. So it cancels out and it is non-polar. Carbon dioxide is non-polar. It's an example of a compound that has polar bonds but is overall a non-polar molecule. Okay, so now that we've identified that, that was the hard part. The easy part is, oh, like dissolves like. Sorry, that hood alarm is going off again. Okay, so since we've identified this as non-polar, this will be more soluble in the non-polar solvent. Now this question is going to be totally different if I ask you which one is more soluble in water. So think about that for a second. Water, you draw the structure or just familiar with water, it's a very polar solvent. So if the question was, which is more soluble in water, the answer would be sodium chloride, more soluble in water because it's an ionic compound, which is polar, and water is polar. So it's really important with this like dissolves like that we're looking at polar and non-polar.